Hello students, welcome back. We are coming toward the conclusion, the culmination of this entire course, the proof of the quadratic reciprocity law, this one here. Previously we went through Gauss' lemma number 1, and then we used it to prove Gauss' lemma number 2. Now we're going to use Gauss' lemma number 2 to prove the main theorem, the quadratic reciprocity law. I don't think we're going to need it, so let's minimize it. Let's go ahead with this proof. Let's keep this one on because we will use it certainly. Okay, this too is a multi-step proof. First, out of nowhere, let's consider a graphical argument. Consider a rectangle in the Cartesian product with a plane, Cartesian coordinate plane with vertices 0, 0 here, and then p over 2 comma 0, p over 2 comma q over 2, and 0 comma q over 2. And the diagonal line that joins 0, 0 and p over 2 comma q over 2, like this. In this particular case, p is 23 and q is 11, and this program is randomized, semi-randomized at least, so you can run over and over again, and then you're going to get each time different pair of integers. Okay, whatever. Now, how many lattice points are there total? Starting from 1, 2, 3, 4, 5, sub 2. Let's see, p over 2 is not an integer, so there's no dot here. So p over 2, 1 before that, p minus 1 over 2. Horizontally, there are p minus 1 over 2 dots. Vertically, q minus 1 over 2 dots. So the this product, the product, p minus 1 over 2 times q minus 1 over 2 lattice points are the total lattice points here. So how many total lattice points here? P minus 1 over 2 times q minus 1 over 2. Okay, all right. And then we have this diagonal line. What is the equation of the line? The slope is q over 2 over p over 2. So it's going to be q over p, right? And running through 0, 0. So the equation of the line is y equals to q over px. In other words, py is equal to qx. And that helps you proving that there's no lattice point on the diagonal, because if so, some x comma y must be in here. Y equals q over px and py equals to qx. And then p must divide x. Euclid lemma. P and q are relative prime. They're primes and they're distinct. So p and q are relative prime. So p must divide x. But then again, if p divides x, x is either 0 or p or something much bigger, but x is being selected from 1 to p minus 1 over 2. That's not possible. So there's a contradiction, so there's no lattice point on the diagonal. Consequently, we get this conclusion. I should not have showed you all this all at once. Let's do only these. The total number of lattice points are the lattice points below the diagonal plus those above the diagonal. There's nothing on it. So below plus above, then I'm going to get the total. Make sense? And the total is, of course, p minus 1 over 2 times q minus 1 over 2. Okay, all right. Now, let's count the number of lattice points below. It turns out this one here gives you below. Let's see. Below, let's highlight it in blue. And above, let's highlight it in green. This is below. And that's above. And let's not worry too much about above because of the symmetry. You can switch x and y basically. Or in this case, I and j. So I is running from 1 to p minus 1 over 2. Yeah, x coordinates running from 1 to p minus 1 over 2. And then the point must be below this line. So j must be, the y coordinate must be below the equation of the line, q over pi. Would you feel a little bit more comfortable if this had been x comma y? X coordinate, and then that's y coordinate. Would you have felt a little bit more comfortable if it had been this? X is running from there, and then x coordinate, y coordinate, and then y coordinate is greater than or equal to 1, and then less than or less than, strictly less than this diagonal. And then again here, well, this just symmetry, so switch x and y. Do you feel a little bit more comfortable if we have xy coordinate like this rather than ij? Well, if you use the indices, then ij look a little bit better, but maybe you can start with xy, x coordinate going from 1 to p minus 1 over 2 for all xy, x coordinate values. Y coordinates begin from 1 up to less than, strictly less than, the point on this diagonal. And then you can switch to I and j later. In any case, what do you get? J is going from 1 to less than this, strictly less than this. This is a fraction. And how many j's are there? We are counting j's 1, 2, 3, 4 up to the greatest integer, not exceeding this, which is precisely the floor function, qi over p. And then I have to repeat that for each I. So vertically, this floor function, qi over p, that many dots vertically for each vertical line. And then there are this many different x coordinates. I is running from 1 to p minus 1 over 2. That's below. And above, well, by symmetry, you can do the same thing. So what did you get? This product is this summation plus that summation. Hence, from Gauss' lemma, the second lemma, p over q times q over p is negative 1 to the... Oh, I need bigger font. Definitely need bigger font. Oh, I got worse. Sorry about that. Okay, all right. Negative 1 to the summation of this floor function qi divided by p, and times negative 1 to the summation this floor function pj divided by q. And if you use the exponent law, you can add up the powers, so summation this plus that. But then again, didn't we just prove from this geometry this blue summation plus green summation is none other than this product? We have it. Here's a proof of the quadratic reciprocity law. I don't know whether Gauss did it this way, to tell the truth. But anyway, I think anybody can see the beauty of this proof. Out of nowhere, somebody thought of this geometrical argument and then associated and got it done with really difficult lemmas. Brilliant, simply brilliant. And then if you look at the end result, look at the simplicity. This is truly a beautiful theorem that you just went through. We already went through the corollary in the first video, the introduction of section 4. So I'll leave you there. And I'll say we are done with section 4, and quite possibly say this entire course is now completed. Maybe I'll consider an appendix, maybe lesson 15 as an application, something. Thank you.